from last week, we know that in the most basic form, executing spatial operations usually involves a map layer input and a map layer output. A map layer is the visual representation of geospatial data in GIS software. Solving a problem often requires a chain of spatial operations executed in a sequence. So this is another example of graphical representation of spatial analysis. Operations are individual components of a spatial analysis. Esri calls all of their tools in ARC Toolbox geoprocessing tools, so you guys should have been exposed to this already. You can access your ARC Toolbox by opening up the ARC Toolbox window, and then a lot of these basic spatial operation functions that we're going to be going over today, you can also bring down from the geoprocessing tab at the top of the screen in ArcMap. So just to go over what we have in this slide really quickly, I want you to become more familiar with these flowcharts. Just a heads up, next week we'll be building on this week's discussion question. I'm asking you to come up with a research question. And so next week I'm going to be having you create a super simple diagram just like this with a flow chart, just describing what you would think you would need to do to help answer that question that you come up with. So again, you're going to have your input layer and it'll flow to that first spatial operation, which is going to give you your first new layer, second spatial operation, and so on until you come up with your potential output. And again, the output from a spatial operation may be spatial. For example, a new data layer is produced, or the output may be non-spatial, where you have a single value or a table as an output. So last week we went over selection, or also known as query operations. So this is a part of that spatial analysis process. So I'm talking about the select by attribute or by location, which we went over when we were covering database management systems and attribute tables. Last week we also went over buffering, which is a proximity tool, and dissolving, which is a generalization tool. And again, buffering is a different type of overlay operation. It's just separated because it has that additional function of proximity. This week, we're gonna go over some of the more basic overlay operations, the clip, intersect, union, and erase functions, and we're also going to review classification, or grouping similar features together for display or analysis. Next week, we'll get more into conversion between data models, such as converting a vector model to a raster model and vice versa. And again, many operations incorporate both the attribute and coordinate data. So for a quick review, a dissolve function is primarily used to combine similar features within a data layer. Adjacent polygons may have identical values for an attribute. It dissolves the boundaries between the features that share the same attribute. This is a generalization tool. Some reasons why you would want to dissolve is it's helpful in removing unneeded information. It reduces storage space and increased processing speed, and prior to applying an area-based selection. So you can kind of see here, you have multiple polygons with different values, and instead of dissecting each of those polygons into smaller units, you're going to combine all of those units into a smooth output polygon, as you can see here. Buffering is an operation that creates a buffer and is useful for proximity analysis. A buffer is a zone around a map feature with an area calculated using distance or time. Buffering may be applied to point features, line features, or polygon features. However, the output will always be a polygon feature. So we have three main types of buffers. We've got the fixed distance buffer, multi-ring buffer, and variable distance buffer. So with the fixed distance buffers, every feature that you're buffering gets buffered by the same distance. When we're doing the multi-ring or nested buffer, you're buffering at multiple distances. This is really useful when different actions are required at different distances. And then we have our variable distance buffer. The buffer distance, as its name describes, is variable and may change among features. And the buffer distance may increase in steps. For example, we may have one buffer distance for a given set of features and a different buffer distance for the remaining features. Volstad states that overlay operations are powerful tools and were an important driving force behind the development of GIS technologies. An overlay operation is a spatial operation in which two or more data sets are superimposed on one another to assess the relationship between features that occupy the same geographic space. Overlay operations also share common elements with other spatial query operations. The primary difference is that overlay operations use a spatial query to create new data sets. So when you perform a spatial query, like select by attribute or location, the output feature data set keeps the same feature geometry, length, area, distance, and they also keep the same attribute table. You're not going to see any difference in that when you're looking at all of your features. When you perform an overlay operation, your attribute geometry changes, therefore your attribute table changes as well. For example, if you were to clip a roads layer to be within a study area, the output data set would only include the sections of roads within that set boundary, resulting in shorter road lengths. And we'll get into this later in the lecture. And again, we've mostly just been looking at vector overlay. Last week we looked a little bit at raster buffer zones, but we're definitely focusing on that vector overlay. So what you're doing with an overlay operation is you're going to have your input layer, and then you're going to have your feature layer, or whatever function you want that input layer to be changed to, and it's going to give you that output of the two overlaid layers, which we'll go over the different types of combinations in the next slide.